In this lesson, I'm going to go into greater detail about stellar parallax. We watched two previous videos which are a good introduction, but we need to understand the theory and the detail a little bit better. As we saw in the prior diagrams, we can see the Earth here and its orbit in two extreme positions 6 months apart. This puts the Earth in the most extreme possible views when looking at stars. The second element is that we have a star that is nearby. It is nearer to us than the background stars. And the background stars are very far away, even in comparison to the nearby star. That's a critical element. As we've seen when we look at a celestial sphere, the stars appear to be fixed on a globe. And these are the stars we're thinking about that are very, very far away and fixed. And so stellar parallax allows us to view a star that is nearby. So as we saw explained to us before, that when the Earth changes its position, this nearby star will appear to change its position in the sky relative to the background stars. So let's see what we mean by that a little more clearly. When we're talking about the background stars, here is the constellation Centaur, where the nearest star is Proxima Centauri. Proxima Centauri, it turns out, is near Alpha Centauri, which is right here, and here is Beta, and here's the Southern Cross. So this is the region of the sky we are looking at. We will look at in the next image. But it turns out that Alpha Centauri and Proxima Centauri are part of a multiple star system. When we look even more closely, we can see here is Alpha Centauri, and there is tiny little Proxima Centauri, a red dwarf, and here is the Southern Cross. And this represents the area that I had marked off on the prior diagram. And this is Beta Centauri right here. And so Proxima Centauri is depicted there. The next thing I want to point out on the scale of on this drawing of the constellation is there's a grid, the latitude-longitude grid. As we can see here on this particular scale, we have 10 degrees. And across this dimension, we have hours marked. Well, an hour turns out to be 15 degrees. So when we get down to this distance down here, there's the 13-hour mark and the 14-hour mark. That represents 15 degrees. So 5 degrees would be about this large. And you may recall in the Celestial Sphere lab, we were trying to get an answer to how far apart on average are the visible stars. So we can see Alpha Beta in this case are about 6 or 7, the other visible stars 1, 2, but certainly more than a degree apart is the distance to the stars. Now a degree, we also learned, can be broken into 60 minutes, and each minute can be broken into 60 seconds. So this is the scale we are talking about when we mean degrees, minutes, and seconds. So what happens when the Earth changes its position and we see a nearby star? This diagram depicts, in this case here, let's say this is the Sun, and here is the Earth in its orbit, and these two locations here, A and B, being 6 months apart. At location A, if we were to look at this nearby star against the distant background stars, the star would appear on this side over here, to the right from viewpoint A, and that's what's depicted here. When we are at A, this is where we see the star. As we revolve in our orbit and come over to this position 6 months later, the star will now appear to be over here, in that location from viewpoint B. viewpoint B would be here. Now the result is, if we take these two pictures, these distant background stars will be in exactly, represented by these three squares, will be in exactly the same position because they are so far away. So the two pictures, when they are overlain with each other, will look like this. When we overlay the two pictures, it will show these two locations, very different locations. So what this means, now we have a very blown up diagram of a star field that we can see here. We have 10 seconds and 15 seconds, so this is a very, very small scale drawing. And these are the very distant fixed stars and or galaxies. So what would happen, comparing to the last picture, is we might see this picture at A and this one at B. Again, referring back to overlaying the two pictures. When we take B and overlay it on A, we see the stars relative to the background. So this is the fixed relative background star that I have selected right here, and you can see A and B would be in different locations. With this scale or grid, we can then measure this distance in degrees, in minutes, or in seconds. And you can see at this scale here, we are talking much less than 1 second. In fact, this here might be 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So in this particular distance here is going to represent about half a second or less. Half a second or less will be the movement. But notice this is one location and this is a location 6 months later. So now let's go back to our large scale drawing to understand the geometry a little bit better. So here again we have this position and this position, and we have the background stars like so, and it's changing its position. In this diagram, one of the things that has been left out is the extension of this line right here. This line should be drawn in as an extension all the way to the background stars. Now when it's drawn all the way to the background stars, we can then clearly identify that the star is here at location A and it's there at location B. We have a grid of degrees, seconds, and minutes, and we can then measure the change in position from A to B. The position from A to B. We define this angle here as the parallax angle P. But you notice that this parallax angle P is 1/2 the measured arc angle between A and B. For simple reasons in geometry, this line and this line form vertical angles. So vertical angles are equal to each other. So this angle equals this angle. And of course we can see here by the symmetry that this is bisected. So this angle here is equal to this angle here. But this is the angle we are primarily concerned about because we're going to study now a right triangle. The right triangle we see depicted here, tracing it in light blue. Here is our 90-degree angle. And we have this parallax angle. What we are looking for is this distance to the nearby star, D. And we know this distance between the Sun and the Earth, 1 astronomical unit. So this then is the opposite side, and this is the adjacent side. So using tangent, the tangent of P then is equal to the opposite over the adjacent. And tan P, the opposite side, happens to be the big distance between the Earth and the Sun. It's 1 AU. And the distance adjacent is the distance to the star. So with this equation, now we have this tangent function, but we have just studied the small angle approximation. And what we learned is that for small angles, sine of theta equals theta in radians. And we also learned that theta equals tan theta for small angles. So if that's the case, then tan P equals P. Okay? So now we have P equals 1 over D. P in this case is measured in arc seconds, and D is measured in parsecs. Those are the units. Arc seconds, parsecs. And so we have this new relationship that allows us to compute the distance to any star that is close enough. It turns out our limits of detectability are about 0.01 arc seconds. So we can see if this is 0.01, then this is about 100. So that's about 100 parsecs. With the advent of some new satellites, we have extended that range up to the 3 to 500 parsec range. But those are the limits because the angles are just infinitesimally small, which you can get a sense of when we are trying to detect angles that small.